Good afternoon, everyone. Thanks for joining us today. The topic of our presentation today is going to be enabling scalable industrial automation. We're going to be talking about the Siemens Industrial Edge and the Industrial Hub environment and how you can really leverage this technology for smart manufacturing. This is brought to you by our Connecticut Smart program. This is part of our series. We will talk to you about the technology first, and we'll hand it over to Siemens, and Flemming and Florian are joining us here today to talk about the technology itself, and then we'll get into a discussion about a specific application of the technology and how we were able to leverage it to create a digital twin for real-time process control. The purpose of today's event is to really help you understand what technologies are out there that are easy to implement and that provide tremendous value for the price point. So we'd like you to really note down any questions that you have during the conversation, during the presentations. We will have two separate sessions that we'll break at specifically to answer questions. So please do keep any questions ready for those. The agenda here for today, again, we're going to take questions at about 1:40 after our first session, describing the Industrial Edge and the Industrial Hub. And then session 2 will begin at 1:45 to talk about the specific application, and then we'll have questions again at 2:25. At the end, we will also go over a couple of state programs and federal programs that are available for small, medium-sized companies. If you have interest in the edge device, if you have interest in the example use case that we're going to present today, we would be more than happy to discuss further on how we can help you to see the true value of the technology through a demonstration project that we can do. This can, depending on the scope of the work of the project, it can be either fully covered or greatly subsidized. And the purpose of this is so that you can really witness the value for your particular application. So again, we'll describe the federal program that's available specifically for that demonstration project. We also have, if you're a Connecticut-based company, grants available to help you purchase the technology. We'll go through several of the grants that are made available at the end of the presentation. So please do stay on. And there's going to be some very valuable information at the end in helping you to actually go from knowing and understanding the technology to what are the resources available to help you gain more specific information about how it can be useful to you, and then even more on how to acquire the technology if you have an interest in moving forward. So at this point, I'd like to introduce Flemming from Siemens, who will discuss the production transparency and optimization for small, medium-sized companies.
Hello, everyone. Can you guys all hear me? I assume you can. And I think I got control of your slides. Yep, all good. Let me just figure out how to get that done. So first of all, Nasir and CCAT, thank you very much for this opportunity to come in and present to this esteemed audience today. It's something we've been long talking about doing, so I'm really happy that we're making this happen. So appreciate the opportunity here. As you just said, my name is Flemming, Flemming Kongsberg for full. Based out in California. I've been with Siemens for a little over 2 years. And partly responsible, one of my many responsibilities here is that I'm trying to figure out how do we create more attraction and transformation for the SMB customers here in the US. And what we'll be talking about today, me at the high level and Florian, my peer in crime here, will come out later at the more detailed level about how we're leveraging industrial edge solutions to do that. So without further ado, let me get started here. And again, we'll take questions later as we go through the presentation here. So If we're looking at the industry as such, it's a very sensitive control I've got here. If we're looking at the industry as such, not just for the small and medium-sized companies here, we all know that there's a ton of challenges that's happening in the industry today. It's getting harder to hire, especially at the right level of quality of people you're potentially looking for. And as more and more elderly people are retiring from the industry here, it's really important that we start early educating the right level of people and making sure that the workforce is able to handle whatever issues comes up in a world that is increasingly complicated and harder to do. I don't think anybody needs to do anything than listen to the news to understand that costs are rising. It's getting more and more expensive to produce things, and that means that it becomes increasingly more important to manage whatever you have from a cost perspective. Optimization, efficiency becomes super important so that the price that you can charge your customers stay within the limit and the reason that they want to pay for that. Complexity is also growing. One of the things that I'm very often talked to is we visited several small and medium-sized companies and talked to CEOs for the last year and a half where we've been going forward here. And you walk into any kind of a plant or a factory out there, this has been built over 20, 30 years with a multitude of different OEMs, machines, and software. And connecting all of those things together as you try to do change becomes increasingly hard and it's complex. So you'd think all these challenges would make your customers more understanding of the challenges that you as a manufacturing company face out there, but no question about it that customers are also becoming more and more demanding what they actually want. So there's a double-edged sword here that makes it even harder. Customers want customization, they want flexibility, they want to have smaller orders. There's a saying out there that every manufacturing companies, even if they're global today, will become an SMB customer very shortly because the needs of a very specific market and the ability to be flexible and move your manufacturing around will become increasingly important. So all of those things are the challenges that a CEO or head of manufacturing or a plant manager is dealing with on a day in and day out basis. And we're trying to see how can we bring a solution to place that helps with that problem. So I just think I skipped a slide there again. This is a very sensitive set of slides here. So there we go. So while you look at all these things today, you might believe that those are individual challenges, complexity, cost, labor. But the important thing is that these can't be dealt with separately. It's not you solve one thing and ignore the others. All of these things have to be done in coordination and they have to be looked at the same place, while at the same time making sure that you actually deliver something that is valuable in a short amount of time in a flexible way. But let's just look at a couple of numbers here. Just going down the same level of 4 parameters that I'm looking at. The U.S. workforce is about $9.1 million unfilled by 2032, at least the data we have, right? And even more importantly, the IT management that is going to be required to implement these challenges. So as elder people who leave the organization, the undocumented efficiency, as we call it, really stays behind. There are no manuals, there are no tools to continue to do that. So it becomes increasingly hard. As I just talked about, costs are going up. We believe that at least up to about 10% of productivity is lost due to stoppages, machines that breaks down, equipment that isn't functioning, parts that don't show up on time. And all of these small challenges leads up to higher and higher costs that becomes more and more important to manage. The complexity, we talked about downtime. I talked about how the improvements are necessary in a smaller environment, even if you're a big company. It is really important that you focus on these things. So whenever there is a disruption, get back up and running becomes increasingly important. And it becomes more and more complex as you're dealing with this multitude of OEMs, machines, and software that's out there, right? And I said, as customers want a different level of flexibility and smaller orders, et cetera, it means that there's more change that happens on your shop floor. And for an organization that is a small and medium-sized companies that might not have skilled IT people to begin with, the question is, where do you even start? And we see at least 45% of the companies that we've surveyed and talked to, they don't do any kind of transformation because they simply don't know where to start. And it's really complex to get even started here. So I'm going to go through in the next couple of slides just three very, very simple examples that some of you may recognize and some of you will see in your own operations. But the challenge here is not exactly on the exact examples here, whether it's a beverage company, whether it's a parts manufacturer, an injection molding company. The problem really is here for you to understand that the solutions we're bringing in place is not vertically fixed to just one solution. They can go into any kind of environment that are dealing with some of those challenges we just talked about. And it really comes down to how do you start pulling the data out from those machines, and how do you start analyzing that data so that you can start making improvement, upskilling your organization, driving efficiencies, and really start driving down the costs that at the end of the day you'll have to transport into your customers at the end. So let's start with each one of these 3 examples here. Oh, keep forgetting that this is a build slide here. Note to self, I gotta fix that. So here we go. So, and of course, then it goes too far. There we go. So, sorry, I apologize. It's a very sensitive set of slides here. So if you're a beverage manufacturer, at the end of the day, you got to put the beverage that you produce into a bottle. And for that, you typically use some kind of bottle automation machines out there. We all see them. I live close to Napa Valley. So yes, I see them from time to time when I head up there. And the thing is really, you got to make sure that the machines that you have deliver the right level of volume to do that. But at the end of the day, sometimes you may do one type of beverage, the next you do the others, you got to change the labels. And every time you do that, you got to clean it, you got to sort it out, you got to change the machines, you got to change the bottle. And that is a downtime that, if it runs late, you might not meet your goals, you might not do this if you're outsourced from another producer to do that. And everything takes time to do that. So if you as a business owner look at that problem, what you really got to think about is how much of my productivity is done as I change from one part to another. And if there's a break into that machinery, you know what, that leads to very, very slow level of deliverables and customers that are potentially waiting to get those orders out the door. And let's not forget that at the end of the day, the energy costs that are still sitting there, that are still running the machine, will continue to drive your bottom line out of the scope that you want to be. So it's super important that you have that real-time set of data that allows you to look at when things go wrong and when the setup happens, that you understand why did it happen, how did it happen, did it happen as scheduled, are we improving the time we do to set up, and really making sure that you deliver against that values that you set up to do. So our solution that we'll talk about in a minute will help you get that set of data coming out of here. The next thing is an example that, let's imagine you have a series of CNC machines that are sitting in it. We talked to a customer a while ago that had 32 machines in multiple different lines. And you got to look at every time you change the setup, you're changing machines again, what we just talked about, changing the setup, changing the machinery. But it's also very important to say that if you've got 2 lines, why is one line doing better than the other? And why is one machine doing better than the other? And if things break on one machine, is there learnings that you can take from one machine to the other machine to continue to update and make sure that whatever breaks down you have, whatever changeovers you have, whatever improvements you make in one area can be scaled out to the rest of your organization or in the rest of the machines you've got as fast as absolutely possible. Because the thing is, if one machine makes a mistake, the chances are that the other ones will be doing the same thing. And it might not be the failure in the machine, it might be a failure in your design. And I think Nasir will give an example of that later in the presentation here. But it really comes down to you need to learn and understand what is happening in order to make those improvements, because every time you have a failure or a downtime or a quality issue, it takes time out of your productivity, and it takes time out of your ability to deliver to your customers' needs and expectations. The last example here is a molding machine. Again, this really comes down to, in the example here, is that you got to make sure that you keep your cost as low as absolutely possible. At some point in time, your molding machines and your blending operations deliver 2 molds per every time you do it. Sometimes it's 4. Well, why is it more productive to do one rather than the other? What is the scrap that's happening in these types of operations? And how can you continuously improve and understand how these things are happening? We talked to a little molding manufacturing the other day, and we asked him, how much scrap do you have, and is that a problem? And he said, well, I've been running this operation for 35 years. I park my car next to the garbage cans out in the back. And when they see overflowing, I start asking, what is happening? Why are we throwing this much material out? So he has the foot on the pedal to understand his business because of experience and been running this for so many years. But he clearly articulated that over time, the next generation of the leaders of his plants might not have that skills, and they're more in tune to looking at this at a dashboard, a set of machinery, and a set of data, rather than just seeing where the garbage cans are being floated and moved around. It is really important that those things are digitalized, that you get the data immediately, so that you don't, for example, look at it for 2 or 3 days before you realize that, wait a minute, my scrap has gone up by 10, 15% over the last couple of days because we changed the product, or we changed the mold, or we changed the formula by which we design our molding processes here. So having that super important, because at the end of the day, if you know what your scrap is, if you know how to reduce it, you can get better and better bits out to your customers that are competitive in a market around that. And if you don't have the data, you have the tendency to get things wrong. So at the end of the day, in order to stay competitive, as I said, it is really important that you start looking at this from a digital transformation. Experience is, of course, important. Having processes in place that you look at these things is important. But it's really important that you get this data correctly, real time, live, so that you can figure out where to even start. Because as I said earlier on, a lot of customers that we talk to, they don't even know where to start. And if you don't know where to start, the tendency is to not do anything. So the really important thing here is to understand what's going on, because if you don't, it's very difficult to figure out how do you transform and how to do it. So we're seeing this as a two-step process, right? The very first thing you need to do is to actually make sure that your machines that you have in your shop floor, the machines that you're using to deliver the outcome and the products to your customers, are connected, that you capture the data, that you capture the usage, that you capture the energy spent, whatever is it that you can get out of those machines from a project signal perspective, and look at that as much as a real-time data. And more importantly, and we talked about with one of our partners this morning, is, yeah, dashboards are great, but not everybody has a tendency to go look at those dashboards, because that's just another thing to do that may not do anything. But how we can set up alerts when things go out of bounds, or when things go up or down outside of the ranges that you predetermined, is almost the most important part. And we can deliver a solution that I'll talk to in a second here, that we can do that without having to do big changes, without having to do big investments, at a very affordable and consumption-based type of an environment to go do that. Because if you have that production transparency, you then have the foundation and the insight to go with the next level of the process here, that's called production optimization. And that is when you start looking at the actual data you're seeing. When do things go out of bound? Which machines are producing better than the other? So you can start doing that root cause analysis to go figure out, how do you actually improve the manufacturing processes that you have, reduce downtime, reduce cost, shorten your changeovers, and with that, you can start driving that continuous improvement. But the foundation here is that you need to have access to the data that your machines produce, regardless of what machine you're using, which OEM has built that machine, whatever that is, so that you don't just look at this in silos, because all of these things are connected across the board. So what we've done, based on the solution that Siemens, of course, provides at a broad scale, and a multitude of solutions that Florian will talk about next here in terms of our industrial edge solutioning. We looked at all the solutions across Siemens. It says there are hundreds, and if not thousands, of different solutions that you can use to build these solutions. But who's got time to go figure out how to build the best solution? Who's got time to figure out all the connectivity edge across all of that? So what we did is that we curated a set of offers within Siemens that you see on the screen here to the right, that gives you the ability to connect to your machinery through different level of standards, that gives you the ability to easily connect and update a dashboard and set up the notifications within the scale you have. And then at the bottom level of the tool here, Florian and his team have built a super innovative tool that we call the quick setup tool, that takes all these various Siemens solutions and get them installed on a local machine, and guidance and manuals to connect to the machinery out there. And we've seen customers do this in less than 30 minutes, going from having zero connectivity to be up and running and being able to do this at a scalable manner. And we offer this as a subscription model, that for 3 months, we can go do it for free. So there's no cost in trying to change, except that you got to find an old computer that sits around on your shop floor or in your IT department somewhere, and the ability to connect to your machines. And then if you like it, you can continue to do that for 3 machines, up to $2,000 a year. And if you have more machines and want to scale it out, we offer really flexible cost plans in order to drive that at scale. So with that, I'm going to hand it back to my peer, Florian, who will tell you more about the specific solutions that we've got. And Florian, over to you. Tell us more about Industrial Edge.
Okay, thank you so much. So my name is Florian Ersch. I'm a principal key expert here at Siemens. I'm actually on the East Coast, so total opposite from Flemming. So but between the two of us, we cover the whole country. And I've been with the company for many years. So I've broad expertise now in terms of what we are offering here and why this is useful. The topic that we're talking about here, which is the enabling platform that Flemming was talking about, is called Industrial Edge. And when we started, Siemens comes from a very strong device and control background. So many machines have PLCs, HMIs, IOs coming from Siemens. But then you always come to the problem that Flemming was talking about. There is more that we need more now, instead of just controlling the machine and telling the machine what to do and how to do it. But really the overarching digital topics on top of it is important. And that needs an ecosystem to manage or to handle. And that is what we call industrial edge. And here we start with introducing a little bit what are the different components that are part of it, our industrial edge ecosystem. It is essentially a digital platform to deliver services and applications close to your control environment. And so you have the central part is what you see here in the bottom right is kind of like you have a device that sits next to your machine, is connected to your machine, and can run then applications. And these are then called the edge apps that are running on top of this. And in order to get the applications to this, it's similar to what you're used to from your phone. We have a centralized system. In this case, we call this the edge management system that you orchestrate and then you can assign which application is going to run on which device on your site. You can centrally buy these applications, similar to, so what kind of like what you saw earlier from Flemming, our specific production optimization bundle, which you can centrally buy this, then it will be visible in your edge management, and then you can assign this to the right device, maybe here in this site B, but then you can also have different sites somewhere else, and you can basically replicate the solution there as well. That means also that if there's any software update that comes in because there's a bug fix in one of the applications, we can just easily roll those out at a time of your convenience to bring these updates, fixes, enhancements close to the field without anybody having to run around, plug in the USB stick, and update. It's all digital in this case. And then also very important, you have access to all of these topics from remote. So you can remotely deploy, you can remotely look at the different applications that are close to the edge, to the device machine without having to go there, like in the case of an HMI that is fixed to it. And so that helps you really a lot in terms of having a more centralized view across sites, what's going on, for all these different apps. And of course, there's diagnostics involved. So in case there are some issues with your device, if you have too many apps deployed and then you run overload situations or so, that is all built in the platform. So again, important part, we have the edge management system, which is there for you to manage your devices that are sitting close to your machines. And we have the edge apps, that is actually the business logic that runs on the edge devices in order to do diagnostics, data collection, anything like this. And then, of course, we have the devices itself that we have. So these are the important terminologies worth remembering because we will come back to them a couple of times. We go to the next slide. We can see now how this actually looks a little bit from a different perspective, from a more architectural perspective. Again, you see the industrial edge device on the bottom right, which is the device attached to your machine. And we have connectivity apps that connect to different automation equipment. That equipment can be Siemens equipment from Siemens PLCs to numeric machines from numeric control, but it can be also any other device from any other vendor. It's not limited to a Siemens world, but really the idea is that the edge connects to any kind of equipment in the field level. So you really have this one aggregated view on what's going on your shop floor. So easily mix and match from PLCs to numeric control, from all vendors to robotics. You can bring all the data from all these different devices, machines, and systems into this edge device. The fact on the more factory level or site level, again, so we see this edge management again. So this is we have different options to manage this. You can manage this as an on-premise solution in your own IT center if you have one, or we can also host it for you in the cloud. And part of the production optimization bundle that Flemming showed you earlier includes already a cloud managed option. So that makes it really easy for you because you really don't need to care about it where it runs. It will just connect to the devices that are on your side. But we give you options, especially if you have a larger, more complex deployments or specific IT security issues. It becomes very interesting to see if you want to run this on your own. But to get started, we recommend just use what we offer in our starter bundle and use the cloud hosted version of it. And then on the top level, we have the Industrial Edge Hub. I didn't talk too much about this earlier, but this is really the app store where you pull the apps from in order to push them to the edge management. So you see here clearly the hierarchy from the field devices on the bottom left to the edge that aggregates this, and then the edge management to orchestrate your site. So how does it now go when we tie this back into Flemming's problem space from earlier? That is something we see on the next slide. You see exactly the same pattern because all of our solutions are now built on that pattern. We have an application that is called Performance Insight that has a web-based front end in which you can then create dashboards to look at different metrics for your production, from OEEs to scrap rates and so on. You can configure that in our Performance Insights app in order to, for what is important. We see a little bit more later how this actually looks like concretely. We have this running on the edge device. And then we have, as you see here on the bottom again, connectivity to either brownfield, greenfield, or anything else that you want to connect to. And it's all harmonized through our industrial edge device and the data management that we have on there. On the next slide, then, we can see, and this is a video, I think, Nasir, if you can try to play it, the video, we can quickly see a little bit how the workflow is. Okay, since the video is not playing, maybe you jump just a little bit into the different section if that is working. Okay, sorry for that. So then let me quickly talk to you through that workflow, and I'll see how we get this information to you in some other way. So what we would see in the video is kind of the workflow, how it works from on the edge management, how you see that there is now the different edge apps that we have. How you then assign the edge app to a specific device, go into the device, and then see what applications are then running on it. We have one application that is called a common configurator application, where you see in there which devices, which physical devices from PLCs or similar you have attached to your edge device. And then you go and configure in this common configurator the different data points that you would want to pull out of your PLC, for example, make that visible inside your edge device, and henceforth enable these data points to be further processed by different applications that you have on your edge device, from performance insights to data managing solutions to connectors that push it into the cloud. All of that is possible. and we have various different connectors. In the demo, you would see connectors from connecting to our PLCs through the Siemens S7 connectivity, through OPC-UA, or even Ethernet IP. So all of these connections are possible in this industrial edge. And you then see also ways how to track which data points come in, what values they have, all in the in this one dashboard. So if you go on the next slide, we quickly recap the benefits and the values of this solution. As on the one hand, we have a very efficient local processing, which is cost effective for you to deploy and run, because it's your device, it's on your site. There's no additional consumption based payment or so. It's all on there. The data is stored there, so there's also no security or risk, because you are under control of your site and of your device. With that, you can also, locally connect to all of the devices. So you have your own technology, you have your domain know-how that you can encode into this connectivity, into the data points that you have here. So you can really capture this and preserve this and make this easily available to others in your organization, or even third parties if you want to. In a way that it's not just the raw bits and bytes in your physical device. And last point I already sort of mentioned, it is data storage, very convenient, but also we have security mechanisms built into this ecosystem that were even quite recently reviewed by UL, and we are certified UL Platinum in this case, that this platform meets also more stringent security requirements for your managing your data. So next we have another demo. I mean, let's see if this video works. If not, Nasir, maybe you can try again. If not, we'll also make it a little bit more quick. What you see here is the performance inside dashboard that we mentioned beforehand, where you can see on your factory level the different different metrics that you have configured. It's fully configurable.
You're breaking up a little bit, Florian.
You can have the different widgets with the dials. You can have
Florian, we're having a hard time hearing you.
Graphs and charts, and then of course.
Sorry, Florian, it's very hard to hear you. I think we lost Florian.
Let's give him a minute to come back in. I've got him on text here. Hopefully he's aware. I think maybe it was all right when we tried to play the video, that probably sucked up his bandwidth. He mentioned they've had some problems in the office today, so let's try not to do the video here.
Okay.
That's probably what's causing the problem. Let's give him a minute. I apologize.
I mean, I can still hear you perfectly fine.
You're back now, Florian. So we'll try to do it without the video, but I think you can keep going here.
Okay. Good. Yeah, sorry for this. I think that last thing I wanted to was trying to explain was that on this dashboard that it's fully configurable, that you have the different dials here. You can see history in here, and you can then easily adapt this to whatever environment you have, and with the data that we have earlier configured in your on your industrial edge device. Yeah, good. Then on the next slide, let's quickly recap on what we have seen so far. Tying back into what Flemming has shown, showed you on the earlier already, is with this, you can get really the transparency of what your production is doing by pulling in all the different data, taking one of the apps that we, like our Performance Insights app that we have shown here, and we to analyze it, make it visible, what is going on your site, in your machine, create dashboards, create reports, and then easily customize that to your need. So you can run this again on this industrial edge device. You can also add your own customizations or logic that you can also deploy on there and really leverage the ecosystem and really pull the different apps together that you would need. And again, it's relatively cost effective to roll out because all you need is a device, PC or similar to get started. Pull the apps there through our Edge Market Hub and Industrial Edge Management System, and then start configuring. And with our quick setup tool, you can really try this out yourself on your laptop, connect it and see if you like it. And if you like it, get a more permanent installation running in your device, in your factory, with an edge device or with a Siemens IPC or similar that we can help you then set up. So, and then let's go to the next slide. We have, of course, a broad ecosystem here that is not only for the performance of your machines, but you can do many other use cases with this ecosystem as well. I mean, part of your performance management and resource consumption, of course, that we already talked about. You have the broader data integration of OT and IT. That is a big topic for everybody. You can have the ecosystem can help you with maintenance of your solutions and production. There's a big AI portfolio that we have now as well in terms of running AI specific AI apps or AI enabled apps on the edge device, for example, for inference of time series, but also visual quality inspection. So basically you hook up an additional camera to your edge device, make picture of parts in your production, and then analyze that on your edge device for quality assurance and report results back into the cloud, into your own or into a standard cloud ecosystem from AWS. And so a little bit newer on the portfolio that we have is that we also have now virtual PLCs and virtual HMIs that you can run on the edge device. So if you have additional control needs that you don't want to have a physical PLC on site configured and running, you can add a virtual PLC that looks and feels very much like a physical PLC, but you have all the advantages of not having to have dedicated cabinet space for it, and maybe have additional flexibility by running it in sometimes in your test environment. And then if you need to move it, you can just virtually move it to your production environment. So this is a really new topic that is coming now more and more, is virtual control and virtual HMIs on the industrial edge ecosystem. And then you can, of course, write your own applications. There are low-code environment that we offer, for example, Mendix, that you can build applications and deploy this on industrial edge. But you can also build something in Python if you want to, and connect it to our data bus, which is based around MQTT. And then, connect to it, process it on your own with your own logic, and then maybe feed that back into your production system, or build your own connectors because you have a dedicated IT system for your order management or so, and then tie that, for example, into a performance-based dashboard. And then if we go, the last slide from my side is really here. You see the different tiles that we have, and this is just a selection of the apps that we have in our ecosystem. But we start on the bottom with connectors that we offer, from connecting to our PLCs to connecting to numeric for CNC machines, to focus and back off, right? As I said before, connecting to also Siemens competitors. Many of those connectors are Siemens connectors that we build and we maintain, but they are also connectors from partners in our ecosystem that deploy and build our own connectors. So if you see a business in that for your side, because you have built a machine or so that will be useful to integrate here, you can do this and also then offer this on the marketplace. On the middle layer, again, we have all these different apps from managing the data locally. This is, for example, this industrial information hub here on the left side is a data manager and data storage, from configuration of the different app from the data, how it works with the common configurator. Flow Creator is really a cool little app that helps you manage small business logic that you need to do when you say, okay, if this happens, then this data point should be triggered. So it's a really easy Node-RED-based logic creation. And then again, on the top layer, all the different apps from analytics, AI, control, and then a whole bunch of third-party applications for really different use cases. So that's all from Siemens side for now. And we said earlier that now we do a quick Q&A on the topics that Flemming and I presented so far.
Florian, there was a question in the chat. Someone asked, does it require a Windows PC or Linux? And then the second part of that was, is the application running on containers?
So if you let's start with if we talk about the productive environment where you really would want to go long term, our recommendation is to go with an industrial PC that runs next to the machine, and on that PC we provide a Linux-based environment that in the end runs then Docker containers. But the system is, due to security reasons, mostly managed. That means you will not really see the Linux or containers, because all you would need to do is say, hey, this application should run here, and then in the background, these Docker containers or so are going to be managed, transferred, started, stopped, all of that for you. For our trial that if you want to do a trial, for example, with our production optimization package that Flemming showed you earlier, you can run this whole system also as a virtual machine on your Windows PC. So we have something that we call a virtual edge device instead of a physical edge device, where you can run this virtually on a VM. And that, for example, would work on a Windows PC. but you can also run it in your IT center if you have a managed environment for VMs. That would also be a good option if you have a larger or more scalable problem to run these also in production. But for trial, run a virtual VM with a virtual edge device on your Windows PC. For production, physical device where there's a Linux inside, and then we manage it for you.
Thank you. If anyone else has any other questions, you can put them in the chat.
I did also, in case we wanted to come back to it in the second session for question and answers, we do have the videos running. So if there's any, Florian or Flemming, if there's any point at which you think it's appropriate to bring those back up, we do have those running now.
Okay.
Yeah, we are on time when we get there.
Then thanks so much for now. I think, as we said, I think we will hang around at the end. If you have more questions, either can talk about it at the end. You can also still put them in the chat here. But then in the meantime, I'll hand it over to Nasir to demonstrate to us here how they are using the Industrial Edge platform in a real-time corrective control application for airfoil machining, really where it shows how to source the data, what intelligence to apply to the data, and then how to effectively react all automatically. It's a pretty cool use case. Thank you.
And again, we'll have another session for question and answers at the end here, just before we get into some of the state program, federal programs, and then the grants that we have available for, at least for the Connecticut manufacturers. So please do note down your questions for the end. But so in this session, as Florian mentioned, we're going to get into discussing how we use the edge device for a specific application. And in this particular case, we want to show how physics models, real-time data that we collect off of the edge device, and post-production inspection enabled adaptive control for airfoil machining. Our goal here was to control manufacturing variability, right? If we're going to produce a batch of airfoils, can we guarantee that each one of those airfoils are going to come out in spec? And more importantly, if we're going to produce a number of airfoils and there is deviation, can we get to the point of understanding the root causes of the deviation, or what are the components that make up that total deviation? And what do we do for correcting for those individual components, right? What are the appropriate parameters to adjust on the machine? So a quick contents of the presentation, we'll go over the experimental setup. We'll look at or have a discussion about the analysis and machine learning side. Right, analysis would be looking at the edge data and then choosing the right machine learning algorithm that is best suited to process that data for the purpose of creating predictive models or surrogate models. So we'll get a little bit more into that in the upcoming slides. Then we will talk about causality analysis. So again, if we're producing an airfoil and that airfoil comes off the machine and we perform inspection and we understand that there's a deviation, right? Depending on, so at specific control points or across the entire surface of the blade, that deviation is comprised of, subcomponents. As an example, we'll get into, is it workpiece deflection, right? Is it tool wear? Is it other sources that are causing the total deviation on that blade? Because if we don't understand the cause, we're not going to be able to apply the right corrective action on the machine, because there's a number of parameters that we can control on the machine. The question here is that which one is appropriate to solve which problem. And you'll see because of the geometry of the airfoil, because of the material, and because of the actual, the thin material that ends up being cut, it's the corrective action changes depending on where you're at in the machining process. And then we'll get into, again, like the appropriate corrective action control, how we actually updated parameters on the machine using OPC UA communication. And then we'll talk about advanced virtual replica and its impact. So this is a high fidelity digital twin. And what can we do with the data we're collecting from the machine in conjunction with physics-based modeling so that we can be in a position to actually create a virtual machining process where we're actually generating virtual edge data. I'll get more into that and why that's useful. So as a matter of scale, the airfoil that you see on the left is 3 inches high and about an inch and a quarter wide as we get to the root of the blade there. The software stack that we used here or the technology stack that we use here from programming to production was using Siemens NX-CAM to actually generate the CNC program to cut this part. We ended up using a 4-axis CNC machine instead of a 5-axis CNC machine. So you'll see some images of the tool path that we used to produce this. Then we actually optimized the tool path using, or analyzed the tool path, I should say, the forces that the tool exerts on the workpiece using third wave production module. And we also actually use third wave distortion as well, which is a module within production module that allows us to see workpiece deflection. And then we use Siemens Run My Virtual Machine. So we have the CNC program generated. We chose certain feeds and speeds. This is Ti 6.4 material. So if anybody's used to machining titanium, you have a very narrow spectrum of the right speeds and feeds to choose to get a successful cutout without inducing work hardening and degrading the life of the tool. So the third wave was also used to kind of analyze the forces and make sure that it kind of helped us to hone in on the right feeds and speeds. The Siemens Run My Virtual Machine was used to actually simulate the cutting process in a virtual environment that had a replica of our controller. So we use, we'll talk a little bit more about the machine we use. The machine had a Cinemeric 1 control, and the Run My Virtual Machine has a digital replica of that machine, its kinematics, but also the exact virtual control, the Cinemeric 1 control. So the logic that's run through that virtual control shows us exactly what the machine would do. So we can cut a virtual part, verify we're not going to get a crash. And you'll see we got some other interesting data out of that software as well. And then the actual cutting of the part on the track machine tool, we have a VMC Tennesci that has a 4th axis on it. So getting into the CNC operations, there was a number of operations before this. Obviously, we're showing operation 9. We had operations 1 through 8 prior to this. The operations prior were, just rough machining. We start out with an 1.25 inch titanium rod as stock material, and then we cut that down to the airfoil shape that you see here. So operation 9 is the operation of interest. This is the operation that we collected data on. This is the blade finishing operation, and so it would have been the most impactful on the eventual dimensions of the blade and the surface quality. So you can see at the top left, it seems like the entire blade is highlighted. It's a little hard to see here probably on the screen, but that's a helic path. So what happens is that the stock material is actually put into the fourth, the three-jaw chuck that's attached to the fourth axis, and it rotates about the X axis. And then the tool comes down and essentially just runs a helic path across the blade for the finishing cut. So the resulting geometry that's cut out of this operation is shown at the bottom left, which is the final, airfoil shape. On the right, we're showing the control points that were used. These are the positions where we measured the deviation of the surface of the airfoil. So we had 30 control points. We had one control point that was on off the blade surface. So 2 through 31 are the control points on the pressure and suction side of the blade. We used a Siemens industrial edge device on this. It was a 427E. The picture there actually is not actually showing the 427E. We actually started off with a 227E, but then we migrated to a 427E edge device. But this picture shows the simplicity of the connectivity to the machine. So you can see on the back of the edge device, there's two Ethernet ports, right? The X1 and the X2 port. The X2 port is an Ethernet connection to the X120 port on the Cinemeric 1 controller on the machine. It's labeled when you go into the control cabinet. You can see the Ethernet switch, and the X120 port is there for communication. So it's as simple as just connecting the X2 port to the X120 port on the machine via an Ethernet. And then the X1 goes out to the internet. And the purpose of that is to connect to the industrial hub. And what the industrial hub allows us to do, we open up a web browser, log into our industrial hub account. We would have already onboarded, right, the edge device, so we can actually access our edge device on the hub. And then we can just browse for applications. And there's two particular applications that we used that we pushed to the edge device for then subsequent installation on the edge device. It was the Cinemeric connector and the Cinemeric data recorder. What these two applications allowed us to do was to actually establish a high frequency communication between the edge device and the CNC controller, and we were able to record and save data on the onboard SSD of the edge device that can then be later exported out for our own analysis. So we wanted to have that capability of collecting real-time data, exporting that out off the edge device, analyzing that, training models, and then running inferencing on the edge device. As Florian mentioned, there's inferencing applications that you can install on the edge device that actually accept Onyx files. So it makes it very, very simple to actually deploy AI on the edge device. This is a quick view. It's not showing all the parameters. We ended up subscribing to 75 parameters on the Cinemeric 1 control at 500 hertz each. So what that means is every 2 milliseconds, we were getting 75 parameters off the machine. So on our particular machine, because it's a 4-axis machine, we have 5 motors. We have the x-axis, y, z, the 4th axis, and the spindle. And each one of those motors, I believe we're getting 6 or 7 different data points. And you can see some of them here. We're getting the commanded speed, the contour deviation, control difference. We're getting the current draw, power, torque, and encoder 1 and 2 positions for each one of the machines. For each one of the axes and the motors. So this is very, very valuable data. And the nice thing here, about this particular application is that it gives us the ability to set up triggers. The triggering was very, very valuable for us because, as you saw on the surface of the blade, we have 30 distinct control points that we're measuring off of. So for each of those control points, we want to make sure that we're looking at the right edge data that's associated with that control point. So, the data that's kind of around, we want to grab the data that's in an area around that control point, so we have contextual information, but also know the data that is recorded for the point at which that cutter is actually right over that control point. So all of this is important information for us when we're feeding it in for model training. This is part of the pre-processing step where we have to do data alignment, making sure that we're actually training and correlating the right portion of the edge data to the end, inspection result, that deviation result, so that we're able to train that, predictive model. So the triggering capabilities on the edge device allowed us to set start and stop recording positions. And so when we're getting close to getting to a particular control point, we can start the data recording and then stop it. In our case, we had two sets of triggers running. One trigger started the recording at the start of the finishing operation and then stopped at the end of the finishing operation. So we have the entire data recorded for the entire cutting path. And then we had separate triggers set up to start and stop recording when we're getting close to, and then when we're getting out of machining over that control point. This is the overall kind of high-level architecture of how everything was set up. So we started off, so if you look at the bottom left, we start off with model-based definition, right? We have a CAD model, the airfoil. We have the control points mapped on the surface where the inspection data is going to be taken from. And then, so that, embeds the position and the requirements for the airfoil within the 3D CAD. Then we have the stock material information. So we have both the material certs, but also measurements of the stock prior to going into the machine. So the diameter, of the stock, the length of the stock, anything that we can capture on the stock material before it goes into the machine, because that will help with causality analysis later. Then we have the edge device connected to the machine that's grabbing real-time data. We not only subscribe to the high frequency variables, but we also were collecting low frequency data, which is any, the overrides that the user would be doing or the operator would be doing on the HMI, on the control itself. So if you're doing feed rate override or spindle speed override or anything of that nature, we're capturing all of that in the low frequency stream. And then we have post inspection. So once that part is produced, we take it off the machine, we bring it over to our non-contact inspection system and scan that blade. So it's that scan data set that we get from inspection that is aligned to the CAD model, and then we extract the deviation. So it's the comparison of where that control point is to where the actual scan data set is. So that surface deviation point becomes very, very important. And that's what we use to correlate with the appropriate, edge data that was collected for that control point. The takeaway here is you want digital data, right? You want digital data from the start. Right? We start off with a CAD model, model-based definition that has embedded the positions of where we're going to take, inspection. And then we're digitizing information about the stock, the edge devices, digitizing information about the manufacturing process itself. And then post-inspection is non-contact inspection, and we're grabbing the actual result of the manufacturing process in a digital form. All of this is being fed into our AI machine learning pipeline for model training. We'll talk more about that. So let's get into a discussion of the causes of deviation. We're talking about an airfoil, and the way we actually had this set up on the machine, typically, I described putting the rod or the titanium stock material in the 3-jaw chuck that's attached to the fourth axis. And typically you would have constrained the tip. In our case, we didn't constrain the tip at all. We left it free. So essentially, this was like a cantilever problem where the tip was kind of free to deflect. We did that purposely so that we can actually induce workpiece deflection. In doing so, we could then really see the value of using the edge device and the data that we collect to come up with a process to actually correct for that workpiece deflection or that tip deflection, right, in real time. But in order to get to that stage, we need to understand what are the causes of deviation. So if you look on the left, we're looking at an airfoil with a tip deviation around 24,000s to 27,000s. And this is on both sides of the airfoil. It makes sense because the tool, when it's at the tip, right, and it's in the the final final machining operation, there's going to be axial and radial forces that are exerted on the workpiece, and those axial forces specifically will actually push the workpiece away, or that titanium or the tip of the blade away from the tool. And so we expect there to be positive material that remains on the blade simply because of that workpiece deflection. So it makes sense that at the tip we have higher deviation, and as we get to the root of the blade, that deviation decreases. On the image, the second image from the left, we get into pathing deviation. And this is something that we discovered through using Run My Virtual Machine. What we did was we posted the operations for cutting this part on the machine through Siemens NX, and then we brought that program in to Run My Virtual Machine on the virtual control. We loaded up our stock material, set up our tools exactly as they were set up on the machine, and we actually virtually cut this part in Run My Virtual Machine. And what we can do after the virtual cut is actually export the cut geometry, and we measured that against the CAD model, and we saw some deviation there. What we ended up realizing was that our setup in NX, our machine kit in NX, had a very, very slight angle difference on our fourth axis than we actually had on the machine. So our virtual, in Run My Virtual Machine had the right setup. Our machine kit was slightly off, and we were able to see the deviation from the posted code. So we call this pathing deviation, and it was due to machine misalignment caused by incorrect fourth axis rotary offset. And then if we get to the third image from the left, this is workpiece deflection, and we get this through simulation. The reason we use simulation was that this is a very, it's dynamic. As you're machining from the tip to the to the root of the blade, there's going to be differences in the way that the workpiece deflects. Obviously, the tip is free, and towards the root of the blade, we have that portion fixed, right, in the three-jaw chuck. But also, as we're machining from leading edge to trailing edge, right, there's thickness differences. We have both twist and camber on this airfoil. And so the deflection is going to be different at the leading edge as it is towards the stacking axis, and more so as we get to the trailing edge. So it's very difficult to measure this with sensors or with like vision sensors. on the machine. We'd have to have a lot of them from different vantage points to be able to capture it in its true sense. So instead, we use physics-based modeling to understand how this workpiece deflects, and we'll talk more about that. And then there's toolware. So this is the last image all the way on the right. And this is measurable. So we can cut a number of parts out, and we can intermittently or in between airfoil cuts, we can measure the tool wear. You know, on a in our case, we use a SensorFAR system. But actually, we additional to the SensorFAR, we actually use the tool setter, and we got into measuring the difference in the tool shape, and I'll get more into that. But this slide essentially, you know, gives us the different components that add up to the total deviation. And each component has its own corrective action that needs to be taken. So if we get a little bit more into the physics-based simulation and actually understanding, you know, workpiece deflection, we used a third wave production module and their NX Exchange. So there's a plugin in Siemens NX. So once we come up with our machining operations, you know, our tool pathing, we can choose the particular tool paths that we want to export out, right, into production module. So there's actually a button in NX via the plugin that allows us. It opens up a little dialog in NX, and it asks us to choose the tool paths, right, the operations that we want to migrate over into production module. It also grabs, right, the tool information. It grabs the stock material information. It grabs the in-process workpiece and all the information that it needs to actually virtually cut the part and run FEA analysis on that cut, so that it can calculate at any instance of time the axial force, radial force, tangential forces, and other information that is important for us to know. Once we get it into production module, right, it goes through the analysis phase, and then we tell it at what points during the CNC process do we want it to run distortion analysis. And that's an additional module within production module that opens up and actually just runs. It takes the machining forces, applies it, you know, at that particular point on the surface of the blade, and then it shows us the workpiece deflection that's caused because of those machining forces at that particular point. So we tell production module exactly the locations that need to be analyzed, and those are the locations of our control point. So it's when that cutter is right over that control point. Okay, so what you're seeing on the screen here are the 6 control points at the tip of the blade. Again, we have 30 total control points, but just for sake of being able to present on the screen here, we're just showing 6 here. So the top row here is showing our initial parameters for machining. So we went with a spindle speed of 917 RPM and a feed rate of 22.8 inches per minute. So that leads to a feet per tooth of about 4 thousandths. And what you can see here is that we have pretty significant distortion caused by the machining forces. So at the first control point, we're at 10 thou. And then as we move through, the cutter reaching kind of the point at which we are kind of in line with the stacking axis, that deviation decreases. And then as we get to the trailing edge of the blade, that deviation increases again. And as we get to the other side of the blade, that deviation again, fluctuates. And what we were able to do in simulation was not only understand the magnitude of the deflection, but we were able to run different machining parameters through to understand how changing the spindle speed and the feed rate affects the total deviation of the part. So at the bottom there, you see our end result. We came to a spindle speed of 3,667 RPM and a feed rate of 15.4 inches per minute, which reduced our feed per tooth to 7/10ths, which significantly decreased the machining forces that were exerted onto the workpiece. And so you see an order of magnitude of deflection change, right? We're much better now in the deflection. And so this physics-based simulation, one, helped us to understand, how much workpiece deflection was contributing to total deviation, but it also allowed us to run a design of experiments and actually come to the conclusion that we can run with a certain feed per tooth that minimizes the deflection. So instead of compensating for the position of the tool, we're actually changing the feeds and speeds on the machine. The drawback, though, is notice that we're going from a feed rate of 22.8 inches per minute, and we've come to a feed rate of 15.4 inches per minute. This is not good when it comes to cycle time, because we're actually increasing the time it takes to produce this part. So if we were to just stick with that spindle speed and feed rate for the entire length of the cut, we would increase the time it takes to produce this part, decreasing productivity, which is not a good thing. And so this makes the case for wanting to do adaptive control. Why not run at a lower feed rate at the tip so that our feed per tooth is low, and gradually increase as we get to the base so that we're recouping some of this time that we're losing because of the decreased feed rate, right? We'll talk more about that, but this is helping us to understand the magnitude of the component of this particular cause of deviation, but then also the appropriate corrective action to take. We were limited, again, in this case, on spindle speed because of the tool manufacturer's recommendation not to go above 3,667 for titanium. Titanium is a very tricky material to machine. It tends to work harden. And as soon as if you work harden the material, now you're actually degrading the life of the tool significantly. And so, we wanted to kind of stick with the highest recommended spindle speed. And so if we wanted to further decrease the feed per tooth, or in other words, increase the surface feed per minute, the only option we have at that point is to decrease the feed rate. So we initially wanted to keep the feed rate at 22.8 inches per minute and just increase the spindle speed to decrease the feed per tooth, but we hit a limit with the spindle speed. And so that caused the necessity to decrease the feed rate. So what we ended up doing was, we ran a number of cuts on the machine, I believe 23 cuts in total. And through those 23 cuts, we collected data on the edge device using the CineMeric connector and the CineMeric data recorder. Again, the CineMeric data recorder allowing us to trigger when to start recording and when to stop recording so that we can collect data that's associated with a particular control point. And then it also allowed us to collect sufficient information about the tool degradation as we were cutting the number of airfoils. So we have tool wear through measurement. We have workpiece deflection through simulation. And then we also understood that there was pathing deviation. And really that came from, it was just simply the difference. So we had a total deviation. And if we added up the tool wear component and the workpiece deflection component, there was still some left over. And that prompted us to actually do an investigation. And when we cut the virtual part is when we realized that actually in an idealized circumstance, if we're running it on Run My Virtual Machine, where you theoretically, in that environment, we don't have workpiece deflection. It's a rigid body. We don't have tool deflection. It's a rigid body. We're simply looking at pathing and how the translation from Siemens NX pathing to a posted code had an effect on the accuracy of the virtually cut part. And so this was a very useful exercise to go through to actually realize that our machine kit was slightly off in the fourth axis position. So that's a one-time fix. The fix for that for the to correct the pathing deviation was to virtually move our fourth axis in the machine kit in NX, repost out the code, recut the part in the virtual environment, and then we were right on. When we physically cut the part, this is what we see for deviation. So you can see a significant change between baseline and after we corrected for pathing deviation. And then the third image from the left, when we optimize to reduce deflection, again, this is increasing the spindle speed, decreasing the feed rate. You can see the tip deflection went down. And so now we kind of have an even deviation across the part. And then when we corrected for tool wear or compensated for tool wear, you can see that the blade was now within tolerance. What we did for tool wear compensation was tool length and tool radius offset. So because we're using a undercutting ball end mill for this finishing operation, and we have a tilt angle on that tool of 25 degrees, meaning we're not cutting right at the tip of the tool, and we're not cutting at the extreme radius of the tool. We're cutting at 25 degrees from the tip of that tool. We have to compensate for both the tool length and the radius because we're at that 25-degree angle. And that was just simple trig that was used to break out the components of tool length and tool radius compensation. So what did this cost us? This costed us, in order to get to this point, we had to machine 23 airfoils. We had invested 57 hours of machine time. We went through 2 ball end mills, which were used for roughing and semi-finishing operations. We went through 13 undercutting ball end mills for the finishing operation. And in total, we cut 172 linear inches of Ti 6.4 material. So these were about 6-inch length of 1.25-inch rods of titanium. So in total, it was 172.5 inches. So you can see that if we were to strictly rely on, collecting, running 23 airfoils and collecting that data on the physical machine, it can be quite costly. We ended up actually using the data from the edge device in another way. And this was to create an advanced virtual replica. So the idea here is that how can we reduce the number of parts we have to physically cut to still get the data that we need to train predictive models for corrective action control? Can we create a virtual replica of our machining process, right, to the point where we can actually generate synthetic edge data? And then can we use that data then in lieu of cutting physical parts? So the way in which we went about doing this was we had to create multiple different models that were focused on specific feedback. The first one was our deflection predictor, right? And this is to understand the deflection component of total deviation. We had to run simulation through production module and Distortion in order to get the workpiece deflection. The question here is that can we train a surrogate model so that we can save time and not necessarily have to run FEA every time, because it takes time to run an FEA analysis. For us, we were, if we were to, when we ran it with the idealized mesh density, it took more than 8 hours to run. If we reduce the mesh density or the element count in the finite element analysis, we did get it down to roughly about half an hour. But because we ran several scenarios through to understand what eventually led to lowering the workpiece deflection, it ended up costing a lot of time. So can we train a model where we can give machining parameters to, and it gives us back the deviation for all of those 30 control points on the surface. And then we get into another model that does tool shape prediction, right? So we want to be able to virtually cut apart, and then we want to be able to see the change in the shape of the tool because of tool wear. And then we have a time series predictor. This is, can we generate power and torque data that we would otherwise get off the edge device by giving the input of the machining parameters and the force data that we get out of the simulation or out of the deflection predictor. Because then that gives us a perfect scenario where we can virtually cut apart. We understand the machining forces through our predictive model, and more so, the model actually gives us back the workpiece deflection for each of the 30 control points. And because we have that force graph, we can take that force graph and the machining parameters being the spindle speed, feed rate, length of cut, depth of cut, and have that time series predictor actually generate the power and torque time series data that we can then compare to actual data that we collected on the machine. So for our surrogate model, we ended up choosing a specific algorithm. It was out of one of the ensemble algorithms that are available in machine learning. And the input to that model was the spindle speed and feed rate, and then the simulation data that we got out of Distortion. So for each of the 30 control points, we had a deviation value. All of those 30 deviation values were input along with the machining parameters to train the model. And what we did was we had one unseen data that we compared against. So this was a spindle speed and feed rate that the model hadn't been trained on or hadn't seen at all. So what you're seeing on the screen here is our ground truth. So the image on the left, control point 24, which is one of the 30 control points that we ran through simulation that took about 32 minutes to run. You can see that our model predicted almost exactly the same value in less than a second. The difference between the simulation deviation and the model deviation was out to 5 decimal place accuracy. And then on the right, you can see two more images. This is off of control point 12, where again we ran simulation, took 32 minutes, but the surrogate model was able to predict it to, again, 5 decimal place accuracy in less than a second. The table in the middle there is showing more, right? We're showing all of the control points. And the two highlighted orange values are the two images that you're seeing on the left and right of the screen. So what this actually just showed us was that there's great potential in running a design of experiments through physics-based simulation, training a surrogate model so that we can essentially almost in real time, give this model the machining parameters, and it would immediately give us back the deviation at each of the 30 control points, thereby giving us that particular component for the total deviation.
Nasir, I
yeah.
just wanted to do a quick time check with you because it's 2:30.
Okay.
And just to make sure you have time for, questions and then the follow-up slide. So just wanted to give you a time check.
Absolutely. Thank you, Dawn. I appreciate that. So the model prediction here for the tool shape, we measured 10 control points off of the tool itself, and we fed in the machining parameters, the spindle speed, feed rate, depth of cut, length of cut, and it gave us this output prediction. You can see at the bottom left there the graph of the progressive tool shape change. So you can see that each of those control points are colored in a different color. And as the length of cut increases, the change in the position of that tool point, that control point changes. So it actually migrates to the inwards towards the center of the tool. This is the results from training our time series data predictor. Again, it takes as input the machining parameters as well as the force graph, and it outputs the predicted power and torque time series data that we would otherwise get off the edge device. So you can see on the left the ground truth, and you can see on the right the predicted. I think we were about 10 watts of total difference between actual and predicted. But what this does is it puts us in a position to virtually cut the part and actually generate synthetic edge data. So what you're seeing on the top left is the Siemens NX virtual cut. On the top right is the production module virtual cut. The bottom left is showing us as we're cutting how that tool shape is changing. It's hard to see it in the actual geometry of the tool, but you can kind of see it in the graph that's to the right of the circular plot there. And then bottom right is showing the real-time deflection of the blade as the machining is happening. Again, both bottom images are going through the predictive models as we're cutting this part virtually. So this puts us in a position where we can virtually cut, hundreds of parts and generate data. We know how the edge data changes as the tool shape changes. So that as the tool wears, the power and torque time series data changes. And because we collected that data on the edge device, and we know exactly the position that they were collected at, not only because we have the information from the encoder position in the edge device, but also from our triggering, and we know that we're within the vicinity, right, of a particular control point. We can come up with this high fidelity digital twin that's able to produce this synthetic data that we can now avoid having to cut a number of parts. So what we're saving here is, now we're down to actually cutting 0 airfoils versus what we were doing before and cutting 23. We're down to 2.5 hours of machine time because we only cut. We ran some carefully designed experiments to run on the machine. They weren't cutting airfoils, but we were cutting the same Ti 6.4 stock material in a spiral type fashion, and we were just focusing on changing the depth of cut and the length of cut, and when we were taking the tool, the tool shape measurements. We ended up not using any ball end mills for this. We only needed to cut the with the tool that we were using for the finishing path. So we ended up consuming 3 ball end mills versus 13. And then we only ended up cutting 22.5 inches of Ti 6.4 material as opposed to 172. But yet we generated so much more data because we were able to set up this virtual twin. So with that, I mean, the takeaway there is, the value that the industrial edge device brought is tremendous, because it not only allows us to understand what's happening during the manufacturing process, it actually, that is the data source, the data that we collect on that system, that enables us to create a high accuracy digital replica of that particular process, right? It's not necessarily migratable if we were to cut a different material or if we were to use a different tool, but for that particular process, it saved us from having to physically cut more parts to collect more data, and set up this virtual twin that was calibrated to produce the same results as we were seeing collected on the edge device. And I'd now like to open it up for any questions that may have come, and then we'll get into resources for Connecticut manufacturers. If you like what you heard about the edge device itself, if you wanted to find out some more information about the specific use case, this was one example of a use case. We'd like to set up other use cases for manufacturing companies so that they can see, real value of adding an edge device or real-time data collection to their processes. We can get into state and federal programs that are available along with grants that are available. But prior to that, are there any questions at this time? Donna, were there any questions in the chat?
No, Nasir, I don't see anything new, but people did ask if they could get a copy of your presentation, and I can also share the recording.
Yep. Okay.
Of this.
So we'd like to have folks on the call, take advantage of, the programs that are put together specifically to help manufacturing companies in adopting advanced technologies to ultimately increase productivity, right? Decrease your costs, increase productivity. And you can look at this as, we talked about real-time corrective action control. I mean, if you have a supervisory control over your manufacturing processes that nearly guarantees you're going to produce a good part every time, you're going to, decrease your scrap rate. It'll increase your acceptable parts per minute or parts per time measurement. And ultimately, it actually helps to save a lot of energy that you would otherwise expend. And so we have several programs available. The Connecticut State program called Digital Transformation, where we can demonstrate, the value of the industrial edge device for you. We can go into specifics of what we did to set up this advanced virtual twin, or we can go into the specifics of how we collect the data, right, on machining the airfoils, how we set up the edge device, how we set up the AI, workflow that resulted in training these predictive models. But we can also get into the digital thread workflow for setting up or generating the CNC program. So the digital transformation has 4 specific subjects: model-based definition, adaptive automation, industrial Internet of Things, and extended reality. So if you have any interest in any one of those technologies, we can demonstrate. We can use our labs here to demonstrate the value of these technologies for you under that program. IBAS Digital Thread Manufacturing is all about showing the value of a digital thread workflow for generating your production programs. So, what I talked about at the beginning, you need to start off with a digital workflow. And using and leveraging model-based definition actually helps to significantly reduce your programming time. If you teach your software the logic of how to generate those programs, right? You teach it the strategies that you would otherwise take. If I have this hole, with this particular tolerance requirement, what machine am I going to put it on? What tool am I going to use? What cutting strategy am I going to use to produce that feature in tolerance? You can actually teach these strategies. We've shown that value in Siemens NX CAM. And the IBEST Digital Thread Manufacturing Program has training, but also we can do company demonstrations and actually help you adopt some of these model-based workflows at your company. And then the Connecticut SMARTE program that I'm going to talk a little bit more on. So I'll move forward here and I'll talk specifically about the Connecticut SMARTE program here. If you want to take a picture of the QR code, this will actually bring you to a form that'll allow you to kind of get in line for us to reach back out to you to set up a smart manufacturing demonstration project. And the Connecticut SMARTE program is funded by the Department of Energy, right? With the purpose of having companies onboard technologies that ultimately will help them save energy. And what we just went through here with the use case, right, and with the specific Siemens Industrial Edge and the Industrial Hub platform, is that you're in a position to very easily add very powerful data collection capabilities to your manufacturing processes. Again, it's an Ethernet connection from the edge device to your machine. We use the numeric connector, but you can use OPC UA. It's an open unified platform. If your controller has an OPC UA server or client on it, it's an easy connection, to the edge device. You can have any controller that has OPC UA communication protocol capabilities, and you can do everything that we just showed here. And so collecting that data, training, predictive models, and then using the inferencing application that can go on the edge device where it leverages your trained model to perform these kind of real-time corrective actions on your machines as you're producing parts, sets you up with this supervisory control that's always looking at your process. You're essentially enabling your machines to have the ability to sense and feel, and then to make decisions on what needs to change to make sure that that part comes out good. And so you're, in essence, you're putting yourself in a position to significantly decrease your scrap rate. And if you look at all of the energy that goes into producing a part that ultimately gets scrapped, it can amount to actually a lot of wasted energy. And what the edge device enables you to do, and hopefully I was able to articulate with the specific use case that I demonstrated, of how we can leverage the data that we get off the edge device, that you can potentially save or eliminate that wasted energy. So this is, we can help to, talk through your particular processes. You can tell us your pain points, and then we can kind of do a solution determination and do a demonstration project either at your companies or here, leveraging our technology center where we have a number of different machines. It can't stop your production in order to see the true value of what the technology can bring for you. We'd love to be able to do these projects for you. Again, we have funding to do this at little to no cost to you. So please do take a picture of this QR code and get in line. We have a year to conduct these projects, so it's going to be short turnaround project. So hopefully we'll be able to show you the value very quickly. Along with the particular program, we actually have grants available to Connecticut-based manufacturers. The size of the companies range from being 100, between 3 and 100 employees, or 3 and 300 employees. Particularly if you're going to take advantage of onboarding technology, and you use the innovation voucher program that gets you up to $25,000. It's a one-to-one cost share on that particular program. That's a perfect funding source to onboard an edge device, right? You can the process there. I'll go through in the next slide. It's very straightforward to get this funding. But the IVP is a really good source to get an edge device. We have the manufacturer voucher program as well. That's up to 100,000. There's different cost share amounts associated with that program. Both are upfront payments, so you should be at the point of getting quotes, not committed or have sent off a purchase order. You want to be at the point of quote, because you have to submit that quote, wait for approval through the portal to get approved for either the IVP or the MVP. And then once you're approved, you can move forward to purchasing. But at that point, you'd have a check in hand through the program for half the amount, up to the max that these programs afford. There's also additive voucher programs. So if you're doing fixturing, right? If you started to incorporate additive into your manufacturing workflows, there's $20,000 to onboard additive technologies. Cybersecurity assistance program, you can get up to $35,000 to assist with cybersecurity assessments and CMMC adoption. And then on the talent training side, right? If let's say you're interested in the technology, you want to go through a demonstration project to see the true value that the technology can bring through the Connecticut Smart program. And you get to the point of wanting to adopt it, and you leverage the grants that are available to help, to offset the cost of onboarding these technologies. You get to the point of wanting to upskill your workforce. So there's additional grants available for Connecticut-based companies for talent and training. So there's an apprenticeship funding program that gives $15,000 in wage subsidy. There's a manufacturing internship program that gives $14,000 wage subsidy. We have digital transformation training, additive technology training through our digital threat training lab. If you want to find out more about these grants, please go to grants.ccat.us. They're all laid out there. I'll just quickly show this slide here. If you focus on the right, it's very, very simple to get money to you. It's 3 steps. You create an account online. So you go to grants.ccat.us. Up at the top right, you'll see sign in. And you can register if you don't already have a sign in. So you create your account, and then 2 is you browse the open grant programs. All the information about the specific grants are there on individual pages for the grants. And then you can select the program and click apply for funding on that page. It's down at the bottom. You'll see a apply for funding button. All of the information that you need to have up front prior to applying is shown above the button. So you'll see the requirements, like the size of the company that you need to be at, some supporting letters that you need from Department of Revenue and Department of Labor. You need to also have a quote in hand for the technology you're looking to onboard. Some grants require. So with that, I'd like to thank you. I'd like to thank everybody for joining us today. I hope this session was helpful. You got an understanding of a technology that's in my opinion very easy to implement. Right, the edge device enables a tremendous amount of data recording capabilities for your manufacturing processes, but the entire ecosystem has ready-to-use applications, so you can see information about your process or run, start leveraging AI through the inferencing application that you can deploy on the edge device. If you want to learn more, feel free to reach out to us. Again, the Connecticut SMART program is there for your benefit. This is our information here. We'll be back in contact with you, after this program. But thank you so much for joining us and for taking time out of your day. We hope this was beneficial to you. Thank you.